Welcome to Lumos. Before we begin, I'd love if you could gently tap that like button. And if you enjoy these calm, wandering science stories, consider subscribing. It helps more curious, sleepy souls find their way here. I always love to hear from you in the comments. Tell me where in the world you are listening and what time your night has become. I find so much joy in those sleepy check-ins. Above you, the stars begin to appear, one after another, until the entire dome of the sky is alive with light. It feels endless, like a sea without shore, like a canvas painted with countless glowing points. You could almost fall upward into it, drifting weightless into infinity. And in this quiet moment, a question rises, a question that humanity has whispered for as long as we have existed. How big is the universe, really? This question is not like others. It is not the kind of question with a neat answer written in a book or a simple number scribbled on a page. It is a question that stretches us, that takes the mind far beyond the familiar boundaries of daily life. When you think of the universe, you are thinking of everything. Every grain of sand on every beach, every tree and every forest, every mountain and river and city. Every planet circling every star within every galaxy, and perhaps even things beyond what we can ever hope to see. To ask how big it all is to peer into the deepest well of mystery we know. For our ancestors, this sky was not just vast, it was divine. They saw gods and spirits written in the constellations. They spun myths of heroes and creatures that lived among the stars. Some believed the sky was a dome overhead, decorated with lights that moved according to the will of unseen beings. Others imagined the heavens as layers stacked upon each other, a staircase of worlds stretching upward into eternity. Without telescopes of satellites, they measured with wonder alone, and yet, in their awe, they were not wrong, because even if their explanations differed, they understood something profound. The universe is greater than us, greater than any one life or generation. But now, with our instruments and equations, we can measure distances not in footsteps or days' journeys, but in light years, the distance that light, moving at 300,000 kilometers every single second, travels in 1 year. Imagine a beam of light leaving a star. In just 1 second, it could circle the Earth 7 times. In 1 year, it has already crossed nearly 10 trillion kilometers. And yet, when we gaze at the night sky, many of the points of light we see have traveled not just 1 light year, but hundreds, thousands, even millions before finally reaching our eyes. The universe is so immense that every glance upward is also a glance backward, a window into the past. The part of the universe we can see, the observable universe, stretches about 93 billion light-years across. Numbers like this hardly make sense to our human minds. We can picture a house, a city, maybe even a continent. But to imagine billions of light-years is like trying to hold an ocean in your hands. You know it's water, you know it's vast, but the scale slips away no matter how hard you try. And yet, that enormous size, that almost incomprehensible expanse, is just the part we can see. Beyond the horizon of the observable universe, there may be more, stretching outward without end. Maybe infinite space, maybe other universes, separate and untouchable. And so, the question, how big is the universe really, is both thrilling and humbling. Every time we believe we've found its edge, every time we map another layer of galaxies or measure another faint signal, we realize there is more. More distance, more mystery, more questions. The universe does not fit into our boxes. It overflows them, breaks them apart, and leaves us standing in awe. This is where our journey begins, with awe. Not with answers, but with the sense of stepping barefoot into a vast ocean, feeling its immensity press against you. In the coming hours, we will wander through the known and the unknown, exploring the galaxies, the cosmic webs, the hidden realms of dark matter and dark energy, even the possibility of multiverses beyond our own. Each step will bring us closer, not to certainty, but to a deeper appreciation of just how grand this cosmos is. So tonight, as you rest, let the question linger softly in your mind. Let it stretch your imagination beyond the walls of your room, beyond the curve of the earth, past the moon, past the sun, and into the shimmering sea of galaxies. The universe is not just large, it is a story that never ends, a horizon that always moves farther as we chase it. And here, with the first chapter of our journey, we begin not with the answer, but with the wonder itself. For sometimes, the asking is the most beautiful part of all. Before modern telescopes, satellites, and powerful observatories, before even the written word, there were eyes looking up at the same night sky we see today. Imagine a small human settlement thousands of years ago. A fire burns in the center of a camp. Beyond its glow, the sky is revealed in its full majesty. Stars stretching across the horizon, the Milky Way shimmering like a river of light. There are no city lights, no smog, no airplanes. The heavens are impossibly clear, and every flicker feels alive. For early humans, the universe was not abstract, it was intimate. The stars seemed close enough to touch, and the sky was woven into their daily lives. To measure the size of the universe, they did not have numbers large enough. Instead, they had stories. In Mesopotamia, people looked up and saw the sky as a vast dome covering the earth. They imagined the heavens as a solid ceiling, holding back the waters of chaos. The stars were thought to be holes, tiny punctures in the dome where divine light shone through. For them, the universe's size was not measured in kilometers or light years, but in layers of meaning. The earth was at the center, the heavens above, and the underworld below, three realms stacked like pages in a cosmic book. In ancient Egypt, the goddess Nut was imagined as the very body of the sky, her arching form stretching over the world, painted with stars. The earth beneath her was Geb, the god of soil, and between them was the air god, Shu, holding them apart. To ask how big the universe was, to them, was to ask how wide could Nut stretch her body. The answer was not mathematical, but spiritual, poetic, and eternal. In India, the Vedic texts spoke of a cosmic ocean upon which the universe floated, infinite in depth and breadth. Time itself was cyclical, measured not in years but in yugas, cosmic ages stretching billions of years, repeating endlessly. Here, the question of the universe's size was entwined with the idea of infinity. The universe was not something to be measured once and for all. It was a rhythm, pulsing, expanding, collapsing, and reborn across time without end. The Greeks, too, sought answers. For them, the night sky was a puzzle that could be solved with reason and geometry. Philosophers like Anaximander suggested the Earth floated freely in space, unsupported, surrounded by rings of fire. Stars and planets glimpsed through vents in those fiery wheels. Later, Aristotle would insist the universe was finite, wrapped in a perfect sphere of stars. To him, beyond the stars lay nothing at all, not even space. Just a limit, a boundary where existence itself stopped. And yet, others disagreed. Archytas, a philosopher of the Pythagorean school, asked a simple but profound question. If you reached the edge of the universe and stretched out your hand, what would happen? If there were a wall, you could touch it. But what lies beyond that wall? If space continues, then the universe cannot have an end. And if it does end, there must still be something outside it. His thought broke open the idea of an infinite cosmos, a concept so vast it unsettled minds for centuries. While myths painted the universe with gods and stories, some early civilizations tried to measure it in practical ways. The Babylonians tracked the motion of the stars with remarkable precision, developing the first star catalogs. They noticed patterns, how certain constellations rose and set with the seasons, how the moon's phases matched cycles of time. In ancient Greece, Aristarchus of Samos made one of the first recorded attempts to measure the distance to the moon and the sun. Using only geometry and shadows during eclipses, he concluded that the sun must be much farther away and far larger than the Earth. Though his exact numbers were off, his insight shattered the comforting idea of a cozy, Earth-sized universe. If the sun was so far and so large, then perhaps the universe itself was unimaginably bigger than anyone had dared to imagine. Meanwhile, in China, astronomers kept detailed sky records that stretched across dynasties. They observed comets, supernovas, and the motions of planets with such care that modern scientists can still use those ancient notes to confirm cosmic events. To them, the sky was not just myth, but an immense clock, its vastness measured through the rhythms of celestial patterns. Despite their differences, what unites all these civilizations is the sense of awe. Whether the universe was imagined as a dome, a goddess, a cycle of rebirth, or an infinite expanse, it always exceeded the scale of ordinary life. It was always bigger, always beyond. And in every culture, the heavens inspired not only curiosity, but also humility. Imagine standing in the desert thousands of years ago, with no telescope, no knowledge of galaxies, no understanding of light years. And yet, when you looked up, you must have felt it. The universe is enormous. Bigger than your village, bigger than your kingdom, bigger than even your gods, perhaps. Before equations and telescopes, before galaxies and cosmic microwave backgrounds, humanity's first answer to how big is the universe was through imagination. They may not have had numbers in the billions, but they had something equally powerful. Stories that gave meaning to the vast unknown. And slowly, very slowly, these stories began to blend with reason. Measurement crept into myth. Curiosity became mathematics. And humanity, though still tiny beneath the stars, began to stretch its reach just a little farther. In the next chapter, we will move deeper into that transition, when the universe shifted from myth to model, when ancient astronomers dared to sketch not gods, but orbits, not stories, but spheres. But for now, let the ancient voices linger. The stories of Nut, of Anaximander, of Vedas Kushans and Babylonian skies. They remind us that the size of the universe is not just a number, but a feeling of standing beneath something so vast that words fall short, and all that remains is wonder. As humanity grew from scattered tribes into civilizations, so too did our questions about the universe grow sharper. Myths, beautiful as they were, no longer felt like enough for some. The stars were still mysterious, but they were also patterns, reliable, repeating, and strangely obedient. And so a new kind of thinking began to emerge, not only asking what the universe means, but also how it works. Imagine standing in ancient Greece around 500 BCE. You're a student listening to the philosophers' debate. The night sky arches above you, the same stars that inspired myths of gods and monsters. But tonight, the question is different. Tonight, your teacher does not ask which god placed the stars there, but rather, by what order do they move? This was the birth of cosmology as a discipline, the attempt to map the heavens with reason instead of only imagination. The philosopher Pythagoras believed the universe could be explained through numbers, that reality itself was made of patterns and proportions. To him, the heavens were not random lights, but part of a grand mathematical harmony. He imagined the planets and stars as spheres, each producing a kind of cosmic music as they moved. Inaudible to our ears, but perfect in its order. This was not science as we know it today, but it was the first glimpse of a universe governed by rules, not chaos. For Pythagoras and his followers, to ask, how big is the universe, was to imagine how far those spheres might extend, how many layers of harmony might encircle the earth. Then came Plato, who believed that the heavens must reflect perfect geometry. He taught that the universe was eternal, unchanging, and built upon ideal forms. The stars to him were fixed points upon the outermost sphere of the cosmos, their perfection revealed in their endless circular motion. Plato's influence was immense. His insistence on perfect circles and spheres shaped astronomy for nearly 2,000 years. The universe was imagined as a nested set of crystalline shells, each carrying the sun, moon, planets, and stars around the Earth. Plato's student Aristotle took these ideas further, solidifying them into a system that would dominate for centuries. To Aristotle, the Earth sat immovable at the center of the cosmos. Around it revolved the moon, the sun, the planets, and finally, the sphere of the fixed stars. Beyond that, he declared, there was nothing, not even space. The universe, in his model, was finite, self-contained, and complete. The stars were not suns of their own, but points of light embedded in a great celestial dome. The size of the universe, therefore, was vast but measurable, a set of concentric spheres, perfectly ordered, with Earth at its heart. This geocentric model was not only philosophy, it was deeply comforting. To imagine the universe as finite, bounded, and centered on us made humanity feel important. The cosmos revolved around Earth because Earth was the stage of creation, the stage of meaning. Centuries later, the astronomer Claudius Ptolemy, working in Alexandria, refined Aristotle's universe into a mathematical system. His Almagest became one of the most influential books in history. Ptolemy described the motions of the sun, moon, and planets with intricate models of circles upon circles, called epicycles. Though complicated, his system worked. It could predict eclipses, the positions of planets, and the paths of stars. For over 1,000 years, Ptolemy's Earth-centered cosmos defined humanity's understanding of the universe's size and shape. In this vision, the universe was vast but finite, ending at the sphere of fixed stars. Beyond those stars, there was no space, no void, only the boundary of existence itself. To ask how big the universe was, under this model, was to ask the size of that great celestial sphere. The answer was unknowable, but it was believed to be large enough to contain the heavens, yet small enough to remain centered on us. Even though these models placed limits on the universe, they also preserved its wonder. Imagine being an ancient student, looking at the night sky with these ideas in mind. To you, every star is embedded in a great crystalline sphere, turning slowly around the Earth. The moon, closer to you, glows as a lantern. The sun, farther still, wheels across the heavens in perfect rhythm. The universe feels ordered, elegant, and purposeful. Though finite, it is grand enough to inspire awe. And yet, some thinkers were restless. Even in the ancient world, there were whispers of other possibilities. Aristarchus, centuries before Ptolemy, had dared to suggest that Earth revolved around the sun. He imagined a universe far larger than anyone could conceive, one where the stars were distant suns of their own. But his ideas were dismissed, too radical for his time. Still, the seeds of doubt had been planted. The question remained, what if the universe was not centered on us? What if it was larger than Aristotle or Ptolemy ever imagined? Part 3 of our journey leaves us in this moment of history, where humanity lives under a dome of stars, confident in a finite cosmos with Earth at its heart. The models of Plato, Aristotle, and Ptolemy have given shape to the sky, comforting in their order, powerful in their predictions. But the story of the universe is not so simple. The heavens have surprises waiting. The orbits will shift, the models will break, and a new revolution is coming, one that will move the Earth itself from the center of everything. In the next chapter, we will step into that revolution, into the daring work of Copernicus, Galileo, and Kepler, who would forever change our idea of how big the universe really is. For centuries, the universe had been imagined as a series of perfect spheres, the Earth resting immovable at the center. This was not just an astronomical model, it was a worldview. To live under Aristotle and Ptolemy's cosmos was to believe that the heavens revolved for our sake, that the drama of existence was staged upon Earth, while the stars and planets were actors bound to their roles. But by the 15th and 16th centuries, whispers of discontent had grown louder. The motions of the planets, carefully predicted through Ptolemy's system of epicycles, did not quite match reality. Observers noticed small discrepancies, awkward details that resisted perfect explanation. The sky, it seemed, did not move with the simplicity that the ancient models promised. And when reality begins to press against belief, change is inevitable. It was in this atmosphere that a quiet revolution began. In 1543, a Polish mathematician and astronomer named Nicolaus Copernicus published a book called De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. Within its pages lay a daring idea. What if Earth was not the center of the universe? What if, instead, the sun sat at the center, and Earth itself was a wandering planet, circling in orbit like the others? This was more than a rearrangement of cosmic furniture. To place the sun at the center was to dethrone humanity from its privileged position. Suddenly, Earth was no longer the still point around which the cosmos turned, but just one body among many, adrift in a much larger stage. At first, the Copernican system did not simplify everything. In fact, his calculations still relied on circular orbits, meaning epicycles remained. Yet, the deeper meaning was profound. By shifting the center away from Earth, Copernicus had stretched the boundaries of the universe outward. If Earth moved, then the stars must be vastly farther away than anyone had guessed, so distant that their parallax, their apparent shifting against the night sky as Earth orbited the sun, was imperceptible to the naked eye. The universe had not only grown in size, it had grown in mystery. Galileo and the telescope. Copernicus planted the seed, but it was Galileo Galilei who watered it with evidence. In 1609, he turned a simple telescope to the heavens, and what he saw overturned centuries of belief. He looked at the moon and saw not a perfect, smooth sphere as Aristotle had claimed, but a rugged landscape, scarred with craters and mountains. He turned his lens toward Jupiter and discovered 4 small moons circling it, proof that not everything in the heavens revolved around Earth. And when he examined Venus, he found that it went through phases like the moon, something only possible if Venus orbited the sun. Each observation was a blow to the old order. The universe was not built upon crystalline perfection. It was rough, dynamic, filled with motion and change. Earth was not unique in having a moon. The heavens were not made for our eyes alone. For these discoveries, Galileo faced resistance. The Church, deeply invested in an Earth-centered cosmos, declared his findings heretical. To suggest that Earth moved was to unsettle more than astronomy. It threatened theology, philosophy, and the very hierarchy of existence. Galileo was forced to recant, confined to house arrest. Yet the truth of his telescope could not be unseen. While Galileo faced censure, another mind in Europe pushed the Copernican model further. Johannes Kepler, using the precise observations of Tycho Brahe, discovered that planets did not move in perfect circles, as Plato and Aristotle had believed. Instead, their orbits were ellipses, stretched ovals, governed by precise mathematical laws. Kepler's laws of planetary motion stripped away the last remnants of Ptolemaic geometry. The heavens were not held by perfect crystalline spheres, but by invisible rules of mathematics, binding planets in their graceful dance around the sun. This was the true beginning of a scientific cosmos, a universe not ordered by myth or philosophy, but by natural law. The Copernican revolution did not merely change the center of the universe, it changed its size. If Earth moved around the sun, then the stars had to be unimaginably far away, so distant that their apparent positions remained fixed despite Earth's annual motion. This realization expanded the universe by orders of magnitude. The dome of stars was no longer a near boundary. It was a distant horizon, perhaps infinite, shimmering beyond comprehension. For the first time, humanity began to sense that the universe was not a closed chamber with walls, but an ocean without clear shores. Earth was not the center, but a drifting vessel. And if that was true, what else might be waiting in the dark, beyond the reach of our eyes? Leaves us at the dawn of modern science. The geocentric comfort has been shattered. The Earth has moved. The Sun has claimed the center. The stars, once thought to be close jewels, are now cast outward into immeasurable depths. The question of how big the universe is has become larger than ever before. For the first time, humans confront the possibility that there may be no boundary at all, no final sphere to contain it. The old universe was finite, ordered, and human-centered. The new one is vast, expanding, and humbling. In the next chapter, we will follow this unfolding story further into the age of Newton, who revealed the invisible hand that moves the planets, and into the age of discovery, when telescopes grew powerful enough to reveal thousands more stars, each whispering that the universe is bigger still. The story of the universe, already shaken by Copernicus, Galileo, and Kepler, was about to undergo another transformation. The idea of a sun-centered cosmos had taken root, but still many questions remained. What force kept the planets in their paths? Why did the moon cling to Earth, never drifting away into the darkness? Why did objects fall downward, always toward the ground? These mysteries seemed separate, scattered, unrelated. It took one man living in quiet contemplation in 17th century England to connect them all. His name was Isaac Newton. Newton was a solitary figure, deeply thoughtful, sometimes difficult, but possessed of a mind that could see connections where others saw only fragments. In 1687, he published a book that would forever change our understanding of the cosmos, Philosophiae Naturalis Principia Mathematica, or simply the Principia. Within its pages lay the key to the heavens, the law of universal gravitation. Newton proposed that the same force pulling an apple to the ground was also the force that kept the moon circling the Earth and the Earth circling the sun. Gravity, invisible and constant, bound the cosmos together. No crystalline spheres were needed, no divine hands pushing planets in their orbits. A single, universal law governed both the smallest drop of rain and the grandest motion of the stars. This revelation transformed the scale of the universe. If gravity acted everywhere, then its reach had no limit. Every star pulled upon every other star across immeasurable gulfs of space. The universe was no longer a stage of isolated actors, but a vast web of attraction, every body connected to every other. But the stars, too, demanded attention. With better instruments, the night sky no longer looked like a simple scattering of lights. Astronomers began to suspect that the stars were not all fixed upon a single dome. They were scattered through three-dimensional space at varying distances, their faintness not a trick of size, but of unimaginable remoteness. Some even speculated that the hazy patches of light seen through telescopes, what we now call galaxies, might be vast star systems of their own, far beyond the boundaries of the Milky Way. Far beyond the boundaries of the Milky Way. The universe was growing larger again, in thought if not yet in proof. Newton himself believed the cosmos was infinite. If it were finite, he argued, gravity would pull everything together in collapse. Only in an endless universe could the stars remain suspended in balance. It was a radical idea, unsettling to many, but it revealed the sheer audacity of human thought in this new scientific age. Consider for a moment how far humanity had come. Just a few centuries earlier, the universe was a set of nested spheres, finite and centered on Earth. Now, under Newton's vision, it was a boundless expanse governed by simple, universal laws. The heavens were not divine machinery, but natural, elegant, and knowable. Yet, this raised new questions. If the universe was infinite, how could the night sky be dark? If stars extended endlessly, why did their combined light not fill the heavens with constant brilliance? This puzzle, known as Olber's paradox, hinted that even Newton's infinite universe had mysteries it could not solve. And so the question of size grew larger still. Was the universe infinite, stretching without end? Or was there some unseen limit, hidden beyond the reach of telescopes? Humanity could now measure the Earth, the Moon, even the distance to the Sun. But the stars, the galaxies, the true scope of everything, those still lay beyond certainty. This was both humbling and exhilarating. For the first time, humans could sense that the universe was not simply big, not merely vast, but perhaps incomprehensibly so. Each discovery pulled the boundary outward, and with each step, the horizon receded further, like a dream that could never be fully grasped. The revolution of Newton and his contemporaries gave humanity new tools: mathematics, observation, prediction. With them, we had begun to tame the solar system. But beyond the planets, in the dim reaches of space, lay mysteries untouched. The 18th and 19th centuries would push us further still, into questions of the stars, the Milky Way, and the strange nebulae that would one day be revealed as other galaxies. The journey was far from over. In fact, it had only just begun. As the 18th century dawned, the universe stretched its mysteries before humanity like an unrolled tapestry. Stars that once appeared as mere pinpricks of light were beginning to reveal themselves as distant suns, each potentially hosting its own worlds. The telescope had grown more powerful, and with it, the capacity for human curiosity expanded beyond the bounds of imagination. William Herschel, a German-born astronomer working in England, took it upon himself to map the heavens with unprecedented ambition. Night after night, he trained his instruments on the sky, counting stars, cataloging nebula, and slowly constructing a picture of the Milky Way. Herschel imagined the universe as a vast, flattened disk of stars, with the sun somewhere near the center. His maps were rough by modern standards, yet revolutionary for their time. They offered the first attempt to grasp the sheer scale of the galaxy, and they implied that humanity occupied a small, almost insignificant position within it. The realization was both humbling and exhilarating. The Earth, once thought to be the center of all, was now just a tiny planet circling an ordinary star in a galaxy of countless others. As the centuries marched on, the universe continued to expand before the eyes of scientists. Astronomers began to notice that some of the faint smudges scattered across the night sky, the nebula, could not be explained as part of the Milky Way. Were these objects gas clouds, as many believed, or could they be entire star systems, galaxies in their own right, far beyond the reach of even Herschel's telescopes? The question hung in the air, unanswered, tantalizing, urging humanity to look deeper. During this period, the tools of measurement improved dramatically. Parallax methods, which used the apparent shift of stars against more distant backgrounds as the Earth moved through its orbit, allowed astronomers to calculate distances to nearby stars. The numbers were staggering. Even the closest stars were light years away, each year representing almost 6 trillion miles. Every calculation expanded the mind, stretching it to comprehend distances that defied ordinary experience. The size of the Milky Way itself was underestimated for centuries. Herschel's original maps, although pioneering, could not account for the vast dust lanes that blocked much of the galaxy from view. It wasn't until the 20th century, with the work of Harlow Shapley and others, that the true dimensions began to emerge. The Milky Way, it seemed, spanned over 100,000 light-years, containing hundreds of billions of stars. And yet, even this realization was only a step toward understanding the universe at large. Beyond the Milky Way lay the question of other galaxies, a concept that would only be proven definitively in the 1920s. At the same time, humanity's perspective on time began to shift alongside our understanding of space. The stars were not static points, they were dynamic, evolving over millions and billions of years. The universe, once thought eternal and unchanging, now revealed itself as a realm of transformation, where stars were born, lived, and died, scattering their material back into space to seed new generations. This cosmic rhythm, invisible yet profoundly real, hinted at a universe alive with processes far beyond human perception. The sense of scale was overwhelming. To imagine a single star at a distance of thousands of light years required stretching the mind into concepts far removed from daily life. To consider the Milky Way in its entirety, hundreds of billions of stars, each a sun in its own right, was to confront a scale of existence that dwarfed the Earth and all its history. And yet, the universe did not end at the edge of the Milky Way. If Herschel could only see a fraction of the cosmos, what lay beyond? For centuries, humanity had measured and mapped, calculated and theorized. The universe had grown from the Earth-centered spheres of antiquity to the sun-centered solar system of Newton, and then outward to the vast stellar disk of Herschel. Each discovery unveiled new questions, revealing both the grandeur of the cosmos and the limits of human comprehension. And so the journey continued, with each generation peering deeper into the night, mapping stars, measuring distances, and contemplating the vastness that surrounds us. The universe was no longer a backdrop for human affairs. It was a stage upon which we glimpsed the scale of existence itself, a stage that stretched beyond imagination, inviting us to explore further, to dream bigger, and to contemplate the magnificent enormity of reality. As the 20th century unfolded, the night sky, once a static and familiar tapestry, revealed its astonishing dynamism. Astronomers began to realize that the faint, misty patches scattered across the heavens were not merely nearby clouds of gas or stars, but entire galaxies, vast islands of stars, each containing billions, perhaps hundreds of billions of suns. Edwin Hubble, peering through the powerful Hooker telescope at Mount Wilson Observatory, made a discovery that would fundamentally reshape our understanding of the universe. By measuring the light from these distant galaxies, he realized that almost all of them were moving away from us. The universe, once considered a fixed and eternal stage, was in fact expanding. This revelation shifted the very notion of cosmic scale. The universe was no longer a static collection of stars. It was a dynamic, ever-growing entity, stretching out in all directions. Distances became almost unfathomable. Galaxies millions, even billions of light years away were now measurable, each one a cosmic city of stars, nebulae, and planetary systems. The light reaching Earth from these far-off galaxies had traveled for millions or even billions of years, carrying with it a story from the past. Looking up at the night sky, we were essentially looking back in time, glimpsing snapshots of ancient cosmic epochs. Consider the sheer enormity of this realization. Our Sun, a relatively ordinary star, is merely one among hundreds of billions in the Milky Way. And the Milky Way itself is only one galaxy among countless others in the observable universe. When Hubble's discoveries were made, the known universe expanded from a single galaxy to a vast, interconnected sea of galaxies stretching across distances that boggle the human mind. Even with modern telescopes, our observations are confined to the observable universe, what we can detect given the finite speed of light and the age of the cosmos. But beyond this observable horizon, the universe may extend endlessly. To grasp the scale, imagine a grain of sand representing the sun. Then picture a handful of sand representing the stars of our galaxy. Now multiply this by hundreds of billions and you start to approach the immensity of the Milky Way. Extend that concept further, imagining billions of such galaxies, each brimming with stars, planets, and unimaginable phenomena.
The human mind struggles to comprehend such numbers, yet they are the reality of our cosmos. But even as we chart galaxies and map the cosmic web, we encounter mysteries that remind us of the universe's complexity. Dark matter, an invisible substance that exerts gravitational influence, permeates galaxies and clusters of galaxies. Dark energy, an even more enigmatic force, drives the accelerated expansion of the universe. These components, together with the visible matter, form a cosmic structure both intricate and grand, a universe far larger and stranger than early astronomers could have imagined.
And within this vastness, our own solar system is but a tiny, fragile island. Earth, circling an ordinary star in an unremarkable corner of the Milky Way, seems insignificant against the backdrop of cosmic scale. Yet it is here, on this small planet, that we have developed the ability to understand and measure the universe. Through centuries of observation, theory, and discovery, humanity has pushed the boundaries of knowledge outward, from the local motions of planets to the behavior of entire galaxies. The night sky invites us to reflect on both humility and awe. Every point of light we see represents vast distances, ancient histories, and untold possibilities. The universe is not just big, it is vast beyond comprehension, a boundless arena of matter, energy, and time, in which our own story is a fleeting and beautiful thread. And as we continue to explore, to observe, and to question, the universe expands not only in space, but also in our minds, inviting us to dream, to wonder, and to marvel at the enormity of existence. And within this vastness, our own solar system is but a tiny, fragile island. Earth, circling an ordinary star in an unremarkable corner of the Milky Way, seems insignificant against the backdrop of cosmic scale. Yet it is here, on this small planet, that we have developed the ability to understand and measure the universe. Through centuries of observation, theory, and discovery, humanity has pushed the boundaries of knowledge outward, from the local motions of planets to the behavior of entire galaxies. The night sky invites us to reflect on both humility and awe. Every point of light we see represents vast distances, ancient histories, and untold possibilities. The universe is not just big, it is vast beyond comprehension, a boundless arena of matter, energy, and time, in which our own story is a fleeting and beautiful thread. And as we continue to explore, to observe, and to question, the universe expands not only in space, but also in our minds, inviting us to dream, to wonder, and to marvel at the enormity of existence. As we continue to journey through the cosmos, we encounter the staggering reality of interstellar distances. The space between stars is not measured in miles or kilometers, but in light years. The distance light travels in a single year, nearly 6 trillion miles. Even the nearest star to our Sun, Proxima Centauri, is over 4 light years away. That means the light we see from that star tonight actually began its journey before we had even celebrated the 20th century. The universe, in this sense, becomes not just a collection of objects, but a vast network of time capsules, each photon of light carrying the history of distant worlds across the void of space. Expanding our gaze further, entire galaxies appear as delicate smudges of light through the lenses of our most powerful telescopes. Yet within those smudges lie billions of stars, each potentially hosting planets, moons, and possibly life. The Andromeda Galaxy, the closest spiral galaxy to the Milky Way, spans over 220,000 light-years and contains more than 1 trillion stars. Our own galaxy is but one of over 2 trillion galaxies in the observable universe, forming a cosmic web of unimaginable complexity. Each galaxy interacts with its neighbors, pulled and stretched by gravity, merging and colliding in slow cosmic dances that span billions of years. To truly grasp this scale, it helps to imagine our solar system as a single grain of sand. The nearest star would be another grain of sand several kilometers away. A single galaxy would be akin to an entire desert. And then, extending this analogy across billions of galaxies, we begin to perceive the almost incomprehensible enormity of the universe. Yet even this observable universe may only be a fraction of the whole, suggesting that beyond the limits of what we can detect, the cosmos stretches infinitely, continuing in all directions without bound. Amidst these vast distances, humans have sought to measure, map, and understand the universe. Instruments like the Hubble Space Telescope have allowed us to see galaxies as they were billions of years ago, giving us a glimpse of the universe's infancy. We study cosmic background radiation, the faint afterglow of the Big Bang, which reveals patterns that hint at the universe's birth and early expansion. Through these observations, we learn not only about where galaxies are, but also about how the universe itself has evolved over 13.8 billion years. And yet, even with these advancements, mysteries remain. Dark matter, which does not emit or absorb light, shapes the formation of galaxies, while dark energy accelerates the universe's expansion. These unseen forces constitute the majority of the cosmos, and their nature remains one of the greatest puzzles of modern astrophysics. Each discovery uncovers more questions, revealing a universe that is not only vast, but also stranger and more complex than our imaginations can fully grasp. The night sky, then, becomes a mirror reflecting our place in the cosmos. Every star, every galaxy, and every beam of light reminds us of the immensity beyond our tiny world. And in contemplating this vastness, we are confronted with a mixture of humility and wonder, recognizing the smallness of our own existence and yet the extraordinary power of human curiosity, which allows us to measure, understand, and marvel at the universe on scales our ancestors could scarcely imagine. As we move beyond galaxies and clusters, we enter a realm where space itself seems to stretch without limit. The universe is not static, it is expanding, with galaxies moving away from each other as the very fabric of space stretches between them. This expansion is so profound that some galaxies are moving away from us faster than the speed of light. It is not that they are breaking cosmic speed limits, but rather that space itself is expanding, carrying them along in its unseen currents. This means that there are regions of the universe that are forever beyond our reach, never to be visited or observed, existing as distant whispers beyond the cosmic horizon. To grasp this scale, imagine the universe as a balloon being inflated. Galaxies are like tiny dots on the balloon's surface. As the balloon expands, each dot moves away from the others, not because they are moving across the surface, but because the surface itself is stretching. In this analogy, there is no center on the balloon. Every point experiences the same recession. Our universe behaves in a similar manner, with no center of expansion, only an ongoing stretching of space that carries galaxies along in a gentle yet unstoppable drift. Even within our observable universe, the distances challenge comprehension. Light from some galaxies has traveled for over 13 billion years to reach us, meaning we see them not as they are today, but as they were billions of years ago, mere infants in cosmic terms. Each observation is a peek into the past, a glimpse of the universe's youth. Stars are born, live, and die. Galaxies collide and merge, and cosmic structures evolve, all while the light travels countless years to reach our telescopes. The cosmos is, in a very real sense, a time machine, carrying us across eons with every glance skyward. But the observable universe is only a fraction of the total. Cosmologists theorize that beyond the limits of our observation lies an unmeasurable expanse, potentially infinite. We cannot see it because light from those regions has not had time to reach us since the beginning of the universe. These regions may contain galaxies, stars, and possibly entire structures that follow physical laws similar to our own, or perhaps laws entirely beyond our current understanding. The totality of the universe could dwarf the observable portion by factors beyond imagination, suggesting a cosmos so vast that our everyday concepts of space and distance scarcely apply. In trying to imagine this, we are forced to confront our limitations. Even the largest numbers we can conceive are dwarfed by the distances between cosmic structures. Our Milky Way galaxy, vast though it is just a single island in a sea of galaxies. Each galaxy, in turn, is composed of billions or trillions of stars, each surrounded by planetary systems, potentially teeming with the unknown. And these islands cluster into superclusters, forming cosmic filaments and voids that weave an intricate web across the universe. The more we learn, the more our sense of scale stretches, revealing a universe that is simultaneously elegant and incomprehensibly immense. As we reflect on this immensity, it becomes clear that understanding the universe is not merely an intellectual pursuit, it is also a meditation. In contemplating the vastness of space, the billions of years of cosmic history, and the sheer scale of distances, we gain a humbling perspective. Our lives, our histories, and even our civilizations are brief flashes within this immense continuum. Yet it is precisely this smallness that makes our curiosity remarkable, allowing us to peer across billions of light years and witness the grand unfolding of cosmic evolution. The universe is vast beyond measure, yet we, through observation, imagination, and inquiry, are part of its ongoing story. As we peer deeper into the cosmos, we begin to understand that the universe is not only vast in space, but also in time. The light we see from distant galaxies began its journey billions of years ago, traveling across the dark, silent void, bringing with it the story of a universe long past. When we look at a galaxy 1 billion light-years away, we are not seeing it as it is today, but as it was a billion years ago, a snapshot frozen in time. Each photon carries a message across the aeons, a whisper from a past that no longer exists, yet shapes the cosmos we inhabit now. The scale of distances becomes almost incomprehensible. Consider the nearest star beyond our Sun, Proxima Centauri, a mere 4.2 light-years away. Even at this relatively modest cosmic distance, light takes over 4 years to reach us. Now stretch your imagination to galaxies hundreds of millions, even billions of light-years distant, each containing billions of stars. The light from these galaxies began its journey when Earth itself was only beginning to form, when life here was still in its earliest, simplest forms. This realization forces us to confront both the immensity of space and the profundity of time. As our gaze stretches outward, we encounter structures of unimaginable scale. Galaxies cluster together, forming groups and clusters which themselves aggregate into superclusters spanning hundreds of light-years. These cosmic cities are interconnected by vast filaments of dark matter, forming a web-like structure that stretches across the observable universe. Between these filaments lie immense voids, regions of nearly empty space, sometimes hundreds of millions of light-years across, reminding us that the universe is not a uniform expanse, but a richly textured, dynamic tapestry. Even with all of this, what we observe is only the tip of the cosmic iceberg. The observable universe, limited by the distance light has traveled since the Big Bang, is vast beyond imagination, yet it may represent just a fraction of the total. Cosmologists speculate that the universe could be infinite, extending far beyond the horizon of what we conceive. There may be regions of space where galaxies form in entirely different patterns, or where the laws of physics play out in ways we cannot yet conceive. Our observable universe is a window, a lens through which we catch a glimpse of a much larger, possibly boundless reality. This leads us to contemplate scale in ways our minds are ill-equipped to grasp. Numbers lose their meaning when describing distances in millions or billions of light-years, and yet they are the only tools we have. When we speak of a galaxy cluster stretching 500 million light-years, or a void encompassing 1.5 billion light-years, we are forced to confront a reality that dwarfs even our most abstract imaginings. Time, too, is measured on a cosmic scale, with the universe itself aged nearly 13.8 billion years, a duration that stretches far beyond any human comprehension. Yet, in the midst of this immensity, we find a sense of connection. Our Milky Way, though a mere speck in the cosmic ocean, is part of a larger story, interacting gravitationally with neighboring galaxies, orbiting within a supercluster, all within a universe governed by the same fundamental forces that allow stars to shine and planets to form. The laws of physics that shape our everyday lives on Earth extend across the cosmos, linking us to phenomena billions of light-years away and providing a bridge between the intimate and the infinite. Contemplating the universe at this scale evokes a mixture of awe, humility, and wonder. We begin to see our place not as the center of all things, but as participants in a vast, ongoing cosmic narrative. The stars, galaxies, and clusters are chapters in a story that spans both time and space, inviting us to ponder the origins of existence and the ultimate fate of the cosmos. In observing the universe, we observe not only its enormity, but also the capacity of our own minds to reach beyond ourselves, to imagine and explore a reality that is as boundless as it is beautiful. As we move beyond what is immediately visible, we enter the realm of cosmic inflation, a period shortly after the Big Bang when the universe expanded at an almost unimaginable rate. During this brief moment, the fabric of space itself stretched faster than the speed of light, carrying energy and matter across distances far beyond what our current telescopes can detect. This rapid expansion set the stage for the large-scale structure of the cosmos, creating the seeds of galaxies and clusters and establishing patterns that would eventually govern the distribution of matter across billions of light-years. The more we probe, the more it becomes clear that the universe is not static. Space itself is stretching, causing galaxies to drift apart over time. Even as light from distant galaxies travels toward us, the expansion of space lengthens the wavelength of that light, shifting it toward the red end of the spectrum, a phenomenon known as redshift. By measuring this effect, astronomers can not only gauge distances to faraway galaxies, but also map the universe's expansion over billions of years. The scale of these movements is staggering, entire galaxy clusters receding at thousands of kilometers per second, carried along by the invisible currents of expanding space. Yet, as vast as the observable universe appears, it may be just a tiny fraction of the total. Beyond the limits of what we can see, space could extend infinitely, containing countless regions where galaxies form, stars ignite, and cosmic dramas unfold beyond our comprehension. Some theories even suggest that the universe could be part of a much larger multiverse, where different regions follow different physical laws, giving rise to realities entirely alien to our own. This speculation challenges the very boundaries of imagination, pushing us to confront a cosmos that may be far grander than we can ever truly experience. Time, too, stretches alongside space. When we observe distant objects, we are peering not only across unimaginable distances, but also backward through time. The light from some of the earliest galaxies began its journey mere hundreds of millions of years after the Big Bang, offering a glimpse of the universe in its infancy. Through these observations, we witness the growth of cosmic structures, the assembly of galaxies, and the formation of stars, processes that take billions of years to unfold. The universe becomes a living archive, a vast and intricate record of change, motion, and transformation on scales that dwarf human experience. Even our own galaxy, the Milky Way, is part of this grand cosmic choreography. Orbiting within a local group of galaxies, interacting gravitationally with its neighbors, and slowly moving toward the Virgo supercluster, it participates in a dance dictated by forces that reach across millions of light-years.
The stars we see in the night sky are just one layer in an immense cosmic tapestry, woven from matter, energy, and the subtle threads of gravity. Each star, each galaxy, is both an individual entity and a part of a larger interconnected whole, reminding us that even in the immensity of the universe, everything is linked. The enormity of the cosmos also compels us to reflect on the fleeting nature of existence. Human life, brief and ephemeral, unfolds against the backdrop of processes that span billions of years. Stars are born, burn brightly, and fade away. Galaxies collide and merge. Black holes form and devour everything around them. Yet, even in this transient universe, there is a profound beauty and coherence. The same physical laws that shape distant galaxies also govern the Earth beneath our feet, the light that fills our rooms, and the beating of our hearts. This unity connects the intimate and the infinite, bridging the gap between human experience and cosmic reality. As we continue our journey, we begin to sense that understanding the universe is not merely about measuring distances or cataloging stars. It is about grappling with scale, with time, and with the profound complexity of existence. The cosmos challenges our minds, stretches our imagination, and invites us to ponder questions that have no easy answers. In contemplating the universe, we confront both our limitations and our capacity for wonder, realizing that curiosity itself is a reflection of the vastness we seek to understand. Each step we take in this exploration brings new revelations, new mysteries, and new opportunities for reflection. From the smallest atom to the largest galaxy, the universe is a testament to the astonishing diversity of forms, forces, and phenomena. And though we can only glimpse a fraction of it, that glimpse is enough to inspire awe, humility, and a sense of connection to something far greater than ourselves. The universe is immense, eternal in ways we struggle to grasp, and yet intimately tied to every question, every thought, every spark of curiosity we carry within us. As we venture further into the depths of space, we begin to realize that the universe is not a random scattering of galaxies, but a vast and intricate web of structure stretching across incomprehensible distances. This cosmic web is composed of filaments, immense strands of galaxies and dark matter that intersect at dense nodes, forming clusters and superclusters, while vast voids, seemingly empty, span millions of light years between them. These voids are not entirely empty, of course. They contain sparse gas and the occasional wandering galaxy, yet their sheer scale reminds us how little of the universe is densely packed with matter. Observing this structure is akin to standing in a forest and realizing that each tree is part of a forest stretching far beyond the horizon, interconnected by hidden roots and networks beneath the surface. Galaxies themselves, once thought to be isolated islands in space, are now understood as components of larger systems that evolve over billions of years. They collide and merge, creating gravitational tides that distort their shapes and trigger waves of star formation. Supermassive black holes at their centers anchor these cosmic cities, influencing the motion of stars and gas, and sometimes sending energetic jets across thousands of light years. The life cycles of galaxies, birth, growth, interaction, and transformation, occur on scales that make human history seem instantaneous by comparison. When we look at the night sky, every point of light represents an entire galaxy, sometimes containing hundreds of billions of stars. Each star a potential solar system, each system a stage for unimaginable possibilities. Dark matter, invisible yet dominant, holds this cosmic tapestry together. Though we cannot see it, we can infer its presence through its gravitational effects on galaxies and clusters. Without dark matter, galaxies would not have formed as they did, and the large-scale structure we observe today would be fundamentally different. Dark energy, even more mysterious, drives the accelerated expansion of the universe, pushing galaxies away from one another at an ever-increasing rate. Together, these unseen forces shape the cosmos in ways that are subtle yet profound, reminding us that the visible universe is only a fraction of the whole, and that our understanding, however vast it seems, remains incomplete. Looking at the observable universe is like peering through a keyhole into a room of infinite size. Light travels at a finite speed, so when we see distant galaxies, we see them as they were billions of years ago. The most distant galaxies are not only incredibly far away, they are ancient relics, giving us a glimpse into the early stages of cosmic evolution. Observations with powerful telescopes reveal galaxies forming just a few 100 million years after the Big Bang, when the universe was a fraction of its current age. These primordial galaxies are small, irregular, and often bursting with new stars, a stark contrast to the majestic spirals and ellipticals we see closer to home. Studying them allows us to trace the history of cosmic structure, witnessing how matter coalesced from a nearly uniform sea of particles into the complex hierarchy we observe today. Beyond the observable universe, speculation takes over. The universe may extend infinitely, containing regions forever beyond our reach. Some models suggest that space could be curved in such a way that it loops back on itself, or that there exist multiple pocket universes within a grand multiverse, each with its own laws of physics. In these hypothetical realms, the familiar constants of nature might differ, stars might shine differently, and life, if it exists, could take forms beyond imagination. While we may never see these regions, the very possibility stretches our understanding of what universe truly means, challenging the notion of limits and boundaries. Time, intertwined with space, further complicates our perception. When we look at a distant star or galaxy, we are witnessing history itself. The light reaching our eyes today left its source millions or even billions of years ago, carrying information about events that occurred long before humans existed. The universe is a living archive of its own past, each photon a messenger from a distant epoch. By mapping these ancient signals, astronomers reconstruct the evolution of the cosmos, from the afterglow of the Big Bang to the assembly of galaxies, stars, and planets, tracing a continuous story that spans nearly 14 billion years. Even within our own Milky Way, the scales are staggering. The galaxy is a flattened spiral, hundreds of thousands of light-years across, containing hundreds of billions of stars. Its stars move in intricate orbits, influenced not only by the visible mass of the galaxy, but by the invisible halo of dark matter enveloping it. The Sun, a seemingly ordinary star, takes 225 to 250 million years to complete one orbit around the galactic center. As we observe these motions, we realize that time and distance in the cosmos operate on scales far removed from our daily experience, offering perspective on the delicate balance and immense forces that shape our corner of the universe. Yet, the vastness of the universe also invites reflection on the fragility and preciousness of life. On a cosmic scale, Earth is a tiny speck orbiting an ordinary star in a quiet spiral galaxy. The conditions that allow life to exist, stable planetary orbits, protective magnetic fields, a temperate climate, are the result of precise cosmic circumstances. Even a slight deviation in these parameters could render our planet inhospitable. In this light, the universe, immense and indifferent, frames human existence in a paradox. We are simultaneously infinitesimal and remarkable, brief and conscious, capable of marveling at the very cosmos that dwarfs us.
The more we learn, the more we understand that the universe is a complex interplay of forces, structures, and processes, stretching across space and time in ways that challenge comprehension. From the smallest subatomic particles to the grandest galactic superclusters, every element contributes to the tapestry of reality. And though we may never explore every corner, never see every galaxy, and never fully grasp the infinite, our curiosity propels us forward.
In the act of observing, calculating, imagining, and questioning, we participate in the universe itself, becoming witnesses to the grandeur and mystery of existence. As we venture further into the study of the cosmos, the staggering enormity of the universe begins to reveal itself in ways that challenge even our most imaginative minds. Beyond the familiar clusters and superclusters of galaxies lies an almost unfathomable expanse, where the interplay of space, time, matter, and energy unfolds on scales that are both majestic and humbling. The universe is not a uniform expanse. It is an intricate cosmic lattice woven from filaments of dark matter and luminous galaxies, separated by enormous voids that can stretch for hundreds of millions of light years. These voids, vast regions of relative emptiness, highlight the paradox of cosmic structure. While matter coalesces in certain regions to form galaxies, clusters, and filaments, other regions remain nearly barren, creating a universe that is both structured and astonishingly vast. Even within these colossal voids, the universe is far from static. Dark energy, the mysterious force driving the accelerated expansion of the universe, is stretching space itself at a rate that continues to increase over time. As a result, galaxies are moving away from one another, and some are receding so quickly that their light will eventually become undetectable to us. This accelerated expansion creates a dynamic, evolving cosmos, where the distances between cosmic structures are not fixed but ever-changing. In this sense, the universe is not merely large. It is growing, expanding, and reshaping itself in ways that challenge our comprehension of scale and permanence. When we turn our gaze to individual galaxies, the enormity of cosmic processes becomes even more apparent. Galaxies are not isolated entities. They are part of a vast cosmic ecosystem, interacting with one another through gravity, collisions, and mergers. These interactions can trigger starbursts where thousands of new stars ignite simultaneously, or send shockwaves rippling through gas clouds, shaping the formation of future generations of stars. Spiral galaxies, with their elegant, rotating arms, are in constant motion, while elliptical galaxies, often the result of past mergers, contain older stars, quietly evolving over billions of years. Even the seemingly empty spaces between stars are filled with gas, dust, and magnetic fields, a complex interstellar medium that plays a critical role in the life cycles of galaxies. The concept of scale in the universe is almost impossible to fully grasp. Consider that our Milky Way galaxy contains over 200 billion stars, yet it is only one of billions of galaxies in the observable universe. Light from the nearest galaxies reaches us in millions of years, while light from the most distant galaxies has traveled for over 13 billion years. When we look at the cosmic microwave background, the afterglow of the Big Bang, we are seeing the universe as it existed nearly 14 billion years ago, a faint whisper of radiation that encodes the conditions of the early cosmos. These observations allow astronomers to reconstruct the history of the universe, tracing its evolution from a nearly uniform, hot, dense state to the vast, structured cosmos we observe today. The universe also challenges our understanding of physics itself. Dark matter, invisible yet comprising roughly 27% of the universe's total mass energy content, exerts a gravitational influence that shapes galaxies and clusters, guiding their formation and evolution. Dark energy, making up approximately 68% of the cosmos, drives the accelerated expansion, and yet its nature remains one of the greatest mysteries in modern science. Ordinary matter, the stuff that makes up stars, planets, and life as we know it, is only a small fraction of the cosmic inventory, a reminder that what we can see is only a tiny piece of the grand cosmic puzzle. Beyond the observable universe, the possibilities become almost infinite. Some cosmological models suggest that space may continue infinitely, with regions forever beyond our observational reach. In this context, the universe we know is just a small bubble within an unimaginably vast expanse. The idea of a multiverse arises, where countless other universes might exist with different physical laws, dimensions, and cosmic histories. While these remain speculative, they underscore a profound truth. The universe is far larger and more complex than our immediate perception allows, and human understanding is constantly pushing against the boundaries of what can be known. Time, intertwined with space, adds yet another layer of complexity. Observing distant galaxies means looking back in time, witnessing events that occurred billions of years ago. Supernovae, the explosive deaths of massive stars, send shockwaves across galaxies, seeding the interstellar medium with heavy elements. These elements eventually form new stars, planets, and perhaps life itself, linking cosmic events across incomprehensible spans of time. Our own solar system is a product of such ancient cycles, a reminder that the story of the universe is also the story of us, written in the language of stars, gas, and cosmic evolution. Even our understanding of distance is challenged by the universe's enormity. Astronomers use units such as light years and parsecs, yet these numbers quickly become almost meaningless when dealing with the scales of superclusters and filaments. The nearest galaxy cluster to our own, the Virgo cluster, is over 50 million light-years away. Yet it is only a tiny part of the local supercluster, itself part of a web of interconnected superclusters spanning billions of light-years. As our observational tools improve, from space telescopes to gravitational wave detectors, we continue to uncover new layers of cosmic structure, revealing a universe more intricate and expansive than anyone could have imagined. In contemplating the universe's size, we are also confronted by our own smallness. Earth, a tiny blue dot orbiting an average star, resides in a galaxy that is itself one of billions in an ever-expanding cosmos. Yet, despite our infinitesimal scale, humanity has developed the capacity to observe, calculate, and understand phenomena occurring billions of light-years away. Through mathematics, physics, and observation, we reach beyond the confines of our planet, touching the very fabric of the cosmos and seeking answers to questions that have captivated our species for millennia. The exploration of the universe is not just a scientific endeavor, it is also a philosophical journey. Each discovery reshapes our perception of reality, challenging assumptions about space, time, and existence. The scale of the universe evokes both awe and humility, prompting reflection on the nature of life, consciousness, and the universe's infinite possibilities. In the grand tapestry of cosmic evolution, we are both spectators and participants, witnessing events that span billions of years while contributing our own fleeting chapter to the story of existence. As we continue our journey into the staggering vastness of the universe, it becomes increasingly clear that the scales we are dealing with surpass ordinary human comprehension. While the observable universe extends roughly 93 billion light-years in diameter, this is merely the portion accessible to our current instruments and technology. Beyond this limit lies the unobservable universe, a realm forever hidden from us because its light has not had sufficient time to reach our telescopes since the birth of the cosmos. The very concept of an unobservable universe challenges our intuition. It suggests that even the immense distances we can measure are but a tiny fraction of what exists, and that the cosmos may extend infinitely, or at least far beyond the horizon of our perception. The observable universe itself is a complex mosaic of galaxies, clusters, filaments, and voids, forming a cosmic web that stretches across unimaginable distances. Galaxies are not randomly scattered. They are arranged in patterns shaped by the distribution of dark matter and the primordial fluctuations that arose in the first moments after the Big Bang. These filaments connect clusters and superclusters like strands of a vast celestial spiderweb, while vast voids, regions nearly devoid of galaxies, highlight the contrast between areas dense with matter and expanses of near-empty space. Some of these cosmic voids span hundreds of millions of light years, reminding us that emptiness is as fundamental to the structure of the universe as the luminous matter that forms stars and galaxies.
Time and distance in the universe are inseparably linked. Observing a galaxy 10 billion light-years away means witnessing it as it appeared 10 billion years ago, long before our solar system existed. In this way, telescopes serve as time machines, allowing us to peer into the infancy of the universe and reconstruct its evolution from the primordial soup of particles to the majestic complexity we see today. Ancient galaxies, smaller and more irregular than modern spirals or ellipticals, reveal the processes of cosmic growth, mergers, and star formation that have shaped the universe over billions of years. Each observation, each faint photon captured from across cosmic time is a window into the vast chronology of existence. The sheer number of galaxies is itself almost unimaginable. Estimates suggest that the observable universe contains over 2 trillion galaxies, each hosting hundreds of billions of stars. Many of these stars have planetary systems, and some may harbor conditions suitable for life. The scale is so vast that even if every human on Earth were to observe one galaxy per second, it would take billions of years to catalog them all. Beyond sheer quantity, the diversity of galaxies is extraordinary. From elegant spirals with winding arms and central bulges, to massive ellipticals formed by countless past mergers, to dwarf galaxies that are mere fractions of the size of the Milky Way. Each galaxy represents a unique history, a record of cosmic processes unfolding over billions of years.
In addition to galaxies, the universe contains phenomena that defy everyday experience. Supermassive black holes lurk at the centers of most large galaxies, including our own Milky Way, with masses millions or even billions of times that of the Sun. Their gravitational influence shapes galactic structure, and their violent activity can release energy equivalent to billions of suns in the form of radiation and relativistic jets. Meanwhile, interstellar gas and dust permeate galaxies, fueling star formation and carrying the elemental building blocks for planets and life. Even regions that appear empty are teeming with subtle activity. Cosmic rays, magnetic fields, and dark matter interact in ways that influence the evolution of cosmic structures over vast timescales. Perhaps the most mind-bending aspect of cosmic scale is the role of dark energy. This mysterious force, comprising roughly 68% of the universe's total energy content, is driving the accelerated expansion of space itself. As galaxies recede from one another at increasing speeds, some will eventually move beyond our ability to observe them, effectively vanishing from our cosmic horizon. This means that the universe we can see today is already a shrinking fraction of what we will be able to observe in the future. The expansion is not through empty space. Rather, it is space itself stretching, carrying galaxies along with it, illustrating the dynamic, evolving nature of the cosmos on a scale that challenges even theoretical physics. Cosmologists also grapple with the concept of the multiverse, a hypothesis suggesting that our universe might be one among countless others. Each universe in such a multiverse could have its own physical laws, dimensions, and cosmic histories, potentially infinitely varied from our own. While evidence for this remains speculative, the idea emphasizes the possibility that the observable universe is only a small bubble within an almost incomprehensibly vast ensemble. Even without invoking the multiverse, the observable universe's scale, structure, and complexity are so immense that they evoke awe and a deep sense of humility in the face of nature's grandeur. Understanding cosmic distances requires not just imagination, but also sophisticated measurement techniques. Astronomers use standard candles like Cepheid variables and Type 1a supernovae to gauge distances across galaxies. Redshift measurements reveal how the universe is expanding, allowing us to map the positions of galaxies in 3 dimensions. These tools have uncovered the accelerating expansion of the universe, a discovery that earned the 2011 Nobel Prize in Physics and fundamentally altered our understanding of cosmic destiny. The interplay of observation, theory, and advanced technology continues to push the boundaries of what we know, revealing a universe more enormous and intricate than anyone could have anticipated.
As we reflect on these scales, the place of humanity becomes both humbling and extraordinary. Earth is a tiny dot in the cosmic ocean, yet our species has developed the intellectual capacity to understand phenomena billions of light years away, to reconstruct the universe's history, and to contemplate its future. From the smallest particle interactions to the grandest cosmic structures, humans are observers of a story that spans nearly 14 billion years and stretches across dimensions beyond ordinary comprehension. Each discovery deepens our connection to the universe, revealing not just our smallness, but also our unique ability to perceive and reflect upon the cosmos. The exploration of the universe is far from complete. As new telescopes, detectors, and computational models come online, we will continue to uncover layers of complexity, from the subtle distribution of dark matter to the formation of the first stars and galaxies. The frontier of cosmology extends not only in space, but also in time, as we strive to understand the universe from its earliest moments to its far future, where cosmic acceleration may isolate galaxies in an ever-expanding void. In this grand journey, every photon we capture, every theory we develop, and every question we ask brings us closer to understanding the unfathomable scale and beauty of the universe.
As we continue to delve into the immensity of the universe, it is essential to consider not only its spatial dimensions, but also the underlying forces and phenomena that have shaped it from its earliest moments. One of the most profound concepts in modern cosmology is cosmic expansion, a brief but extraordinarily rapid expansion of space that occurred within the first fraction of a second after the Big Bang. During this period, the universe grew exponentially, stretching from subatomic scales to macroscopic dimensions in an instant. Inflation explains several puzzling features of the universe we observe today, such as its remarkable uniformity, the large-scale structure of cosmic filaments, and the apparent flatness of space. Without this dramatic early expansion, galaxies might never have formed, and the universe as we know it would be entirely different. Beyond the initial expansion, the universe has been shaped by gravitational forces, acting over incomprehensible distances and timescales. Gravity, though relatively weak on small scales, becomes the dominant architect at cosmic scales, guiding the motion of stars within galaxies, galaxies within clusters, and clusters within superclusters. This invisible hand sculpts the cosmic web, dictating where matter accumulates and where vast voids remain nearly empty. The interplay between gravity and dark energy, the mysterious force driving accelerated expansion, creates a dynamic tension in the cosmos. While gravity seeks to pull matter together, forming stars, galaxies, and clusters, dark energy stretches space itself, driving the accelerated separation of cosmic structures over billions of years.
The fabric of space and time is not a static stage upon which cosmic events unfold. It is a dynamic, malleable entity shaped by the mass and energy it contains. According to Einstein's general theory of relativity, massive objects warp the surrounding space-time, causing the gravitational effects we observe. This warping is not merely a theoretical concept. It manifests in measurable phenomena, such as gravitational lensing, where the light from distant galaxies is bent and magnified by intervening mass, and in gravitational waves, ripples in spacetime caused by cataclysmic events like merging black holes or neutron stars. The detection of these waves, first achieved in 2015, opened a new window into the universe, allowing astronomers to listen to cosmic events that would otherwise remain invisible. Time itself becomes an intricate factor in understanding the universe. Observing distant galaxies means looking back in time, often billions of years.
allowing us to reconstruct the universe's history in remarkable detail. Ancient galaxies, formed just a few 100 million years after the Big Bang, appear tiny and irregular, contrasting sharply with the mature, spiral, and elliptical galaxies we see closer to home. By studying these distant systems, scientists can trace the formation of stars, the growth of supermassive black holes, and the gradual enrichment of the interstellar medium with heavy elements, processes that ultimately lead to the emergence of planets and potentially life. The universe is, in essence, a living history book written in light across the cosmos.
Another mind-boggling aspect of cosmic scale is dark matter, an invisible substance that does not emit, absorb, or reflect light, but exerts a profound gravitational influence on visible matter. Without dark matter, galaxies would not have the rotational speeds we observe, and the large-scale structure of the universe would look entirely different. Dark matter forms the scaffolding upon which galaxies are built, and while we cannot see it directly, its presence is inferred from its gravitational effects. This invisible component constitutes roughly 27% of the universe's total energy content, dwarfing the mere 5% of ordinary baryonic matter that forms stars, planets, and living beings. Cosmic distances are so vast that our minds struggle to grasp them. Light, traveling at 299,792 kilometers per second, still takes billions of years to traverse from one galaxy to another. Measuring these distances requires ingenuity, from using standard candles like Cepheid variables and Type A supernovae to mapping redshifts that reveal the universe's expansion. These measurements not only inform us of how far away objects are, but also illuminate the dynamic history of the cosmos, showing how galaxies have moved, clustered, and evolved over billions of years. The universe is not only vast, but also vast and dynamic. Supernova explosions scatter heavy elements into space, fueling the next generation of stars. Black holes, ranging from stellar mass remnants to supermassive behemoths at galactic centers, influence the motion of stars and the growth of galaxies. Pulsars spin at incredible rates, emitting beams of radiation that sweep across space like cosmic lighthouses. Quasars shine with the energy of billions of suns, powered by material falling into supermassive black holes billions of light-years away. Each of these phenomena represents the universe's extraordinary range of conditions and scales, from the minuscule to the colossal. As the universe continues to expand, the observable horizon shifts, gradually isolating distant galaxies from our view. Future civilizations, billions of years from now, may see a vastly emptier sky, with most galaxies receding beyond detectability due to accelerated expansion. In this context, the universe is not only immense but transient in terms of what can be observed. Our era, by cosmic standards, is unique. We exist at a time when the universe's structure is both visible and accessible, allowing us to study galaxies, clusters, and cosmic microwave background radiation before they fade from view. Finally, contemplating the universe's scale brings a profound philosophical perspective. Humans occupy a tiny corner of the cosmos, yet our curiosity, intellect, and ingenuity allow us to comprehend phenomena spanning billions of light-years and billions of years. We are observers, capable of decoding the cosmic story, from the birth of the first stars to the accelerated expansion of space, and perhaps even to the ultimate fate of the universe. The enormity of the universe challenges our imagination. Yet it also highlights the remarkable capabilities of human understanding, reminding us that even as small beings on a tiny planet, we can grasp the vast tapestry of existence stretching across space and time. As we move even further into the cosmic ocean, the concept of distance begins to warp in our minds. The universe is not just vast in space, it is vast in time. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago, a young structure in the infancy of the cosmos.
The light we see now has traveled longer than the entire existence of human civilization, crossing voids and threading through the vast cosmic web that binds matter together. Time and distance intertwine, and in contemplating them, we begin to grasp that the universe is not simply big in a linear sense, it is multidimensional in its magnitude, a tapestry woven from both space and epochs. These distances are not uniform. Some galaxies cluster together tightly, forming gravitationally bound groups where stars and planets are densely packed. Others drift in immense voids, isolated across millions of light-years of near-empty space. These voids are not empty in the absolute sense. They contain dark matter, faint gas, and the occasional wandering galaxy. But they are vast enough that a solitary observer could travel for millions of years before encountering another star system. The cosmic landscape is therefore a mosaic of dense nodes and endless stretches, a network of complexity that challenges our ability to visualize it.
Yet, in this grand complexity, there is also rhythm and structure. Cosmic filaments, vast strands of galaxies and dark matter, stretch across hundreds of millions of light-years, connecting superclusters like threads in a web. At the intersections of these filaments lie massive galaxy clusters, gravitational anchors that shape the flow of matter around them. Between the filaments lie immense cosmic voids, regions where few galaxies form and where dark energy exerts its subtle influence, pushing the universe outward at an accelerating pace. Observing this structure, we see not chaos, but a delicate order emerging from fundamental forces that have shaped the universe since its earliest moments. The scale becomes even more astonishing when we consider the ultimate reach of the universe. Beyond what we can observe lies an unknown expanse, perhaps infinite, containing regions of space that will forever remain hidden from us. The light from these regions has not yet, and may never, reach our telescopes. This unobservable domain may contain galaxies, stars, or structures beyond comprehension, suggesting that the total size of the universe could be unimaginably larger than what we currently map. Even the cosmic horizon, the edge of our observable universe, is only a fraction of the total, like peeking at a vast ocean through a single porthole. In contemplating this immensity, we confront a humbling truth. Human perception is but a tiny spark within this vast cosmos. Yet, despite our smallness, we possess the ability to probe the depths of space, to measure distances across billions of light-years, and to unravel the history of the universe from its fiery beginnings to the present. Every discovery, every telescope image, every piece of cosmic data expands our understanding, giving us glimpses into a reality far beyond our everyday experience. The universe is immense, intricate, and majestic, and through patient observation and imagination, we become part of its grand story, however brief our place within it may be. As we venture further into the cosmos, the concept of distance begins to take on a new, almost surreal dimension. Light, the fastest traveler in the universe, is our only guide through this vast expanse. Yet, even light is limited by the constraints of space-time. When we observe a galaxy a billion light-years away, we are not seeing it as it is today, but as it existed a billion years ago. Its light has journeyed through empty voids, past clusters of galaxies, and across invisible threads of dark matter, only to reach our telescopes now. Every observation of the distant universe is, in essence, a glimpse into the past, a window into moments long gone, and yet eternally preserved in photons racing toward us. The universe expands continuously, stretching the very fabric of space itself. This expansion means that distant galaxies are not simply moving away from us, they are being carried along by space as it grows. The farther a galaxy is, the faster it appears to recede. Some galaxies, beyond a certain distance, move away faster than the speed of light due to this expansion, rendering them forever beyond our reach. The observable universe, limited as it is, represents only a fraction of the total, a bubble of light and matter that we can access.
Beyond this cosmic horizon lies an uncharted realm, perhaps infinite, whose secrets remain hidden, teasing the imagination with possibilities we can barely begin to fathom. Within this immense scale, patterns emerge. Galaxies cluster into groups in superclusters, connected by filaments of dark matter and separated by vast cosmic voids. These structures stretch across hundreds of light years, forming a web-like skeleton that defines the large-scale architecture of the universe. Gravity, the invisible sculptor, weaves this cosmic tapestry, guiding the motion of galaxies and shaping the evolution of clusters over billions of years. Observing these patterns, scientists begin to understand the profound interplay between matter, energy, and the unseen forces that orchestrate the expansion of space. Yet, even as we map these structures, we are humbled by the enormity of what remains unseen. Dark energy, a mysterious force permeating space, accelerates the universe's expansion, pushing galaxies ever farther apart. Its nature remains one of the greatest enigmas in modern cosmology, a silent influence dictating the fate of the cosmos. In the presence of such vastness, human concerns shrink, yet our curiosity soars. Through mathematics, observation, and imagination, we bridge the gap between our tiny world and the infinite beyond, tracing the contours of a universe that stretches beyond comprehension.
In reflecting on this, one begins to grasp that the universe is not just physically immense, but conceptually boundless. Our understanding is constantly evolving, shaped by each new observation, each new insight, and each daring hypothesis. To contemplate the universe is to confront both its enormity and our own smallness. Yet in this confrontation lies a quiet joy, the realization that even a fleeting spark of consciousness, like ours, can reach across the void and touch the infinite.
The deeper we journey into the question of the universe's true size, the more we encounter not only vast distances, but profound mysteries that challenge the very edges of human understanding. The observable universe, spanning about 93 billion light-years in diameter, is already almost unfathomably large. Yet it is important to remember that this is only the part we can see, the portion of the cosmos from which light has had enough time to reach us since the Big Bang, some 13.8 billion years ago. Beyond this observable boundary lies an expanse we cannot touch, regions where galaxies, stars, and perhaps even entire structures exist, but whose light will never arrive. The very concept of an edge to the observable universe is not a true edge of existence, but a horizon, a limit defined by time, light, and the nature of expansion itself. This horizon is called the cosmic light horizon. Imagine standing on a shoreline, gazing out at the ocean. The curve of the Earth prevents you from seeing beyond the horizon, but the ocean itself continues far past where your eyes can reach. In the same way, the universe extends far beyond our cosmic horizon. Galaxies beyond this boundary are still there, but their light is forever cut off from us by the relentless expansion of space. In fact, as space expands, more and more distant galaxies are carried away so quickly that their light will never catch up. Over time, the observable universe will shrink in practical terms, not because it is getting smaller, but because fewer galaxies will remain visible to us.
This raises profound questions about the true scale of the universe. Is it finite, looping back on itself like the surface of a sphere? Or is it infinite, extending without end, filled with galaxies far beyond our view? Current observations suggest the universe is flat on large scales, which may imply that it could be infinite. If so, the portion we see is but the smallest sliver of an endless reality. If it is finite, then it may wrap around in ways that defy simple human geometry. Perhaps light could, in theory, circle the cosmos and return to us, though in practice, expansion prevents such possibilities. Even within the observable universe, the numbers themselves inspire awe. 2 trillion galaxies, each containing hundreds of billions of stars, and around those stars, countless planets. The distances are so immense that our own galaxy, the Milky Way, though vast at 100,000 light-years across, is a mere fleck in the larger canvas of superclusters. The Laniakea supercluster, which includes the Milky Way, spans over 500 million light-years and contains around 100,000 galaxies. And yet, even Laniakea is just a small part of the greater cosmic web, a network of filaments and voids stretching across billions of light-years, like threads of a grand tapestry. These structures did not appear instantly. They are the result of nearly 14 billion years of cosmic evolution, seeded by minute fluctuations in the density of the early universe. Inflation magnified these tiny variations, and gravity then amplified them, pulling matter into knots and filaments. Over billions of years, galaxies formed along these strands, while enormous voids emptied out. To observe this cosmic web is to see the fingerprints of creation itself, imprinted on scales beyond imagination. Yet, perhaps the most astonishing idea is that the universe we see may be just one bubble in a far greater multiverse. Some cosmological theories suggest that inflation may have produced not just one universe, but countless others, each with its own laws of physics, constants, and histories. If true, then our already vast universe is but a single drop in an infinite sea of universes. Though speculative, the concept highlights the limits of what humans may ever truly know. The universe is not just large, it may be endlessly layered, infinitely branching, and fundamentally beyond full comprehension. And yet, even as the cosmos stretches into incomprehensible immensity, there is something profoundly grounding about our ability to study it. From a tiny planet circling an ordinary star on the edge of a modest galaxy, we have developed the tools to measure galaxies billions of light-years away, to detect the faint afterglow of the Big Bang, and to trace the expansion of the universe itself. In this vast theater, humanity is small, but our curiosity allows us to reach across the gulf of time and space, drawing meaning from the endless dark. The universe is not only big, it is boundless, not just in physical size, but in mystery. To contemplate it is to recognize both our insignificance and our uniqueness, both our fragility and our extraordinary ability to look outward, to question, to wonder. And so we continue, step by step, light year by light year, thought by thought, into the endless night. As we journey deeper into the question of the universe's immensity, we inevitably begin to ask not only how vast it is right now, but also how it will unfold into the far future. The size of the universe is not static. It has been growing since the Big Bang, and its growth is governed by forces that remain only partially understood. To grasp the true magnitude of the cosmos, we must look beyond the present moment and stretch our imagination billions, even trillions of years into the future. Let us begin with the simple fact: the universe is expanding. This was first discovered by Edwin Hubble in 1929, when he observed that galaxies are moving away from us, and the farther away they are, the faster they recede. This observation led to the realization that space itself is stretching, carrying galaxies apart. But what came later was even more surprising. In the late 1990s, astronomers using supernovae as cosmic distance markers found that not only is the universe expanding, it is expanding faster and faster. Some unknown force, which we now call dark energy, is driving this acceleration. Dark energy makes up about 70% of the energy of the cosmos, and yet we have almost no idea what it truly is. It acts as a repulsive force, countering gravity on the largest scales, ensuring that the expansion does not slow down, but instead accelerates. If this acceleration continues indefinitely, the universe's size will not just grow, it will become unimaginably, almost inconceivably vast. To understand how vast, consider this. Every second, the observable universe gets about 70 kilometers larger in every direction.
In 1,000,000 years, that adds up. In 1,000,000,000 years, it is staggering. And over trillions of years, it becomes something beyond human comprehension. Galaxies that we can see today will drift farther and farther away, carried outward by the expanding fabric of space. Eventually, their light will be stretched so much by the expansion that it will fade away, slipping beyond our cosmic horizon. Astronomers predict that in about 100 billion years, all galaxies outside of our local group, the Milky Way, Andromeda, and a handful of smaller galaxies, will have disappeared from view. They will not have ceased to exist, but their light will be so redshifted, so faint, that no observer in the far future will ever detect them. To those future beings, the universe will appear much smaller than it really is. They may believe, wrongly, that their galaxy is the only one that exists, just as we once believed the Milky Way encompassed everything.
The universe, in other words, plays a trick. The bigger it gets, the less of it we can see. Expansion hides its immensity. But let us push further, beyond even the billions of years. In the deep future, when the stars of the Milky Way have burned through their fuel, when galaxies have become graveyards of white dwarfs, neutron stars, and black holes, the universe will still be expanding. Black holes will dominate, slowly consuming whatever matter drifts too close. Over time, even black holes will evaporate through a process called Hawking radiation, releasing their mass back into the universe as faint streams of energy. After unimaginable timescales that make the current age of the universe look short, only a thin mist of low-energy particles and photons will remain, scattered across an ever-growing void. This is sometimes called the heat death of the universe, a state where everything is spread so thin, so evenly, that no structure, no star, no planet, and no spark of complexity remains. The universe will still exist, but it will be vast, cold, and dark, a silent ocean of almost nothing. Its size by then will be effectively infinite compared to today. The universe, in other words, plays a trick. The bigger it gets, the less of it we can see. Expansion hides its immensity. But let us push further, beyond even the billions of years. In the deep future, when the stars of the Milky Way have burned through their fuel, when galaxies have become graveyards of white dwarfs, neutron stars, and black holes, the universe will still be expanding. Black holes will dominate, slowly consuming whatever matter drifts too close. Over time, even black holes will evaporate through a process called Hawking radiation, releasing their mass back into the universe as faint streams of energy. After unimaginable timescales that make the current age of the universe look short, only a thin mist of low-energy particles and photons will remain, scattered across an ever-growing void. This is sometimes called the heat death of the universe, a state where everything is spread so thin, so evenly, that no structure, no star, no planet, and no spark of complexity remains. The universe will still exist, but it will be vast, cold, and dark, a silent ocean of almost nothing. Its size by then will be effectively infinite compared to today. So, how big is the universe, really? The truth is that we cannot say. It is bigger than we can see, bigger than we can measure, and perhaps bigger than we can ever truly imagine. Its immensity stretches not only across space, but across time, across possibility, and across realms of physics we have only just begun to glimpse. And in the midst of this incomprehensible scale, here we are, tiny, fragile beings, orbiting a small star in a small galaxy, daring to ask questions that reach beyond the edge of space and time. The universe is not only immense, it is humbling. To consider its size is to recognize both our smallness and our greatness. For though we occupy almost nothing of its space, our minds are vast enough to attempt to contain it.
Throughout history, the question of the universe's size has not only been a scientific puzzle, but also a profoundly human one. When we ask, how big is the universe really, we are not just looking for numbers or distances, we are asking about our place within it. The story of how human beings have tried to measure the immensity of the cosmos is as fascinating as the cosmos itself, because it reflects both our limitations and our endless curiosity. In the earliest days of human thought, the universe was imagined as small and ordered. Many ancient cultures believed that the earth was flat, with the heavens above and the underworld below. The sky was seen as a dome, studded with lights, and beyond it was often thought to lie gods, spirits, or an endless void. To those early observers, the universe was no larger than what their eyes could see. The sun rising and setting, the stars wheeling overhead, the moon shifting through its phases. To them, this was the totality of existence.
As civilizations advanced, so too did their cosmic imaginations. The ancient Greeks began to argue about the size and shape of the universe. Some, like Aristotle, believed the universe was finite, with Earth at its center and the stars embedded in crystalline spheres. Others, like Archytas and later Epicurus, speculated that space might stretch out forever. These were radical ideas, centuries ahead of their time, hinting that the universe could be far larger than anyone could perceive. During the Middle Ages, most people still believed in a geocentric universe, Earth at the center, surrounded by planets and stars in concentric circles. But with the Renaissance came a revolution. Nicholas Copernicus dared to place the sun at the center, pushing Earth into the ranks of the planets. Galileo, with his telescope, shattered the crystalline heavens, revealing mountains on the moon, moons orbiting Jupiter, and countless stars invisible to the naked eye. The universe, it seemed, was already much bigger than we had thought.
The real turning point came with the work of astronomers like Johannes Kepler, Isaac Newton, and later Edwin Hubble. Newton's laws showed that gravity worked the same in the heavens as it did on Earth, uniting the cosmos under one set of principles. Then, in the 20th century, Hubble's discovery that galaxies are racing away from us and that the universe is expanding suddenly expanded our vision from a single galaxy to billions. What had once been thought of as the universe turned out to be just our local neighborhood, a single island in a vast cosmic ocean. Today, with modern telescopes and satellites, we know the observable universe stretches about 93 billion light-years across. And yet even this enormous number is not the full story. It is only what we can see, limited by the age of the universe and the speed of light. Beyond that horizon may lie more galaxies, more structures, perhaps an infinite expanse. The true size of the universe may never be knowable.
But here lies something profoundly human. Though we may never measure the universe in its entirety, our imagination allows us to reach for it. When we stand beneath the night sky, when we point our telescopes toward distant galaxies, when we build theories to describe what we cannot see, we are stretching our minds across that immensity. We are bridging the gap between the finite and the infinite. And this perspective also reshapes how we see ourselves. For much of history, humans believed we were the center of creation, that the universe was built for us. But the more we have learned, the more we have realized how small we are in scale. We are a speck orbiting an average star in an average arm of an average galaxy among billions of galaxies. And yet, there is beauty in this humility, because in recognizing our smallness, we also recognize something greater, our capacity to wonder, to question, to dream. The universe may be immense beyond comprehension, but it is through us, tiny, fragile beings, that it becomes aware of itself. Carl Sagan once said, "We are a way for the cosmos to know itself." And in many ways, that is the ultimate answer to the question of size. The universe is not just measured in kilometers or light years, but in the depth of our curiosity and the breadth of our imagination. So when we ask, how big is the universe really? We are also asking, how big can our minds become? And the answer, like the cosmos itself, may be without limit. If we are to understand the immensity of the universe, we must look closely at the tools humanity has built to measure it. For most of our history, the stars were far beyond our reach, silent lights we could only wonder at. But in the past century, our instruments have become windows, allowing us to see farther, deeper, and more clearly than ever before. Through these tools, we are slowly piecing together just how vast the cosmos really is. The first great leap came with the telescope. Galileo's small refractor in the early 1600s opened the door, revealing that the night sky contained far more stars than the naked eye could perceive. But the telescope has grown from a small tube of glass to immense machines like the Keck Observatory in Hawaii and the Very Large Telescope in Chile, each capable of capturing faint whispers of light from galaxies billions of light years away. Perhaps the most iconic of all is the Hubble Space Telescope, launched in 1990. Orbiting above Earth's atmosphere, free from the blurring effects of air, Hubble has given us the deepest images of the universe ever captured. When astronomers pointed it at what seemed to be an empty patch of sky, they discovered thousands of galaxies hiding in the darkness, some so far away that their light began its journey billions of years ago. These images, known as the Hubble Deep Field and Ultra Deep Field, changed forever our sense of the universe's scale. What looked like nothing turned out to be an ocean of galaxies. And Hubble is only the beginning. In 2021, the James Webb Space Telescope was launched, carrying even more powerful instruments. With its enormous mirror and sensitive infrared detectors, Webb can peer through cosmic dust, revealing the earliest galaxies formed just a few 100 million years after the Big Bang. It is not just showing us how big the universe is, it is showing us how it grew, how galaxies assembled, how stars were born, and how structure emerged from chaos. But telescopes are not our only tools. Astronomers also listen to the faint afterglow of the Big Bang itself, the cosmic microwave background radiation. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, this radiation fills the universe like a quiet echo, a leftover heat from when the cosmos was just 380,000 years old. With satellites like COBE, WMAP, and Planck, scientists have mapped this radiation with extraordinary precision. These maps act like a blueprint of the early universe, showing tiny ripples in density that later grew into galaxies and clusters. By studying this faint light, we can measure the age, composition, and size of the universe with remarkable accuracy. Through these observations, we have learned that the universe is about 13.8 billion years old, and that the observable portion stretches some 93 billion light-years across. We have also discovered that the cosmos is made not only of stars and galaxies, but also of dark matter and dark energy, mysterious ingredients that shape its expansion and fate. Beyond telescopes and radiation maps, humanity has found new ways to measure distance. We use the brightness of certain stars, like Cepheid variables and supernovae, as cosmic mile markers. We track how galaxies move, how their light stretches and shifts, giving us clues to their distance and speed. And now, with gravitational wave observatories like LIGO and Virgo, we are beginning to listen to the universe in an entirely new way, detecting ripples in spacetime caused by colliding black holes and neutron stars. Each ripple adds another piece to our cosmic puzzle. What all these tools reveal is both staggering and humbling. The more we build, the more vastness we uncover. Each telescope, each satellite, each new detector stretches the boundary of what we can see, but the horizon always remains out of reach. For every galaxy we capture, there are countless more beyond, waiting in the dark. In this way, measuring the universe is not just a scientific endeavor. It is an act of human imagination and persistence. We take fragile instruments built by human hands and aim them into the infinite, asking questions no other creature on Earth has ever thought to ask. And with every answer we uncover, the universe grows larger, deeper, and more mysterious. The cosmos is vast beyond comprehension, but our tools give us glimpses, tiny windows through which we peer into eternity. And though we may never see it all, each glimpse reminds us of something profound. We are small, yes, but we are also explorers, stretching our reach across billions of light years, mapping the immensity of the universe one photon at a time. When we speak of the size of the universe, it is natural to imagine it in terms of distance, light years, kilometers, horizons that stretch farther than our eyes or instruments can see. But to truly grasp its immensity, we must also think in terms of time. For in the cosmos, space and time are inseparably woven together. Every time we look outward into the night sky, we are not only looking across unimaginable distances, we are looking back into history. This is one of the most extraordinary facts about the universe. Light does not travel instantaneously. It has a speed, fast beyond ordinary imagination, 300,000 kilometers per second, but still finite. That means the light we see carries with it a record of when it was released. When you look at the moon, you are seeing it as it was about a second ago. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at the nearest star system, Alpha Centauri, you are seeing it as it was more than 4 years ago. And when you look at distant galaxies through powerful telescopes, you are seeing them not as they are now, but as they were billions of years ago. This transforms the night sky into something far more profound than a static image. It is a time machine. Each star, each galaxy, each faint smudge of light is a message sent long ago, arriving only now. The farther we look, the older the message. Our universe reveals itself to us in layers of time, like pages in a cosmic history book. Consider this: the farthest galaxies we have ever observed through the Hubble and James Webb telescopes show us the universe as it was when it was less than 1 billion years old. We are seeing newborn galaxies, fragile structures just beginning to form. When we study them, we are not studying how they are today. We are studying how they were long before our Earth, our Sun, or even our Milky Way fully existed. The cosmic microwave background radiation takes this time-traveling vision even further. This faint glow, spread evenly across the sky, comes from a time when the universe was only 380,000 years old. Before that moment, the cosmos was a hot, opaque soup of particles and radiation. No light could travel freely. But when the universe cooled enough for atoms to form, light was released, and it has been streaming through space ever since. When our instruments detect that faint microwave signal, we are literally seeing the oldest light in the universe, a baby picture of everything, captured when it was in its infancy. So when we ask, how big is the universe really? The answer must include this extraordinary dimension. The universe is as large in time as it is in space. Its 13.8 billion years of history are spread across the sky like a tapestry. Every night we look up, we are gazing into the depths of that history, seeing not one universe in one moment, but countless universes in countless moments, layered upon one another. And here lies a beautiful paradox. The farther we look, the closer we come to the beginning. Imagine standing in a vast hall of mirrors, where each reflection shows you not only another place, but another time. That is what the universe offers us. Look at a nearby star, and you see the recent past. Look at a distant galaxy, and you see a cosmic youth. Look at the microwave background, and you see the dawn itself. The entire span of cosmic history is written into the light around us, waiting for us to read it. But there is also a limit. Beyond a certain distance, beyond the cosmic horizon, we cannot see. Light from those regions has not had time to reach us because the universe has not existed long enough. This boundary defines the observable universe, a sphere centered on us, not because we are special, but because light takes time to travel. The true universe may be much larger, perhaps infinite, but our vision is bounded by time itself. Thinking in this way gives the universe a different kind of immensity. It is not just billions of light years wide, it is billions of years deep. To explore it is not just to measure distances, but to peel back layers of time, to trace the story from the first fireball of the Big Bang, through the rise of galaxies and stars, to the moment we find ourselves in now. And there is another wonder in this perspective. We, fragile beings of flesh and thought, living on a small planet orbiting an ordinary star, are capable of reconstructing this grand history. By studying faint glimmers of light, tiny ripples in radiation, and patterns in galaxies, we can reach back almost to the beginning. In a way, our minds stretch farther than our bodies ever could. We may never touch those distant galaxies, but in our thoughts, in our equations, in our telescopes, we hold them close. So how big is the universe? It is as large as 13.8 billion years of history spread across space and time. And to measure it is to travel not only outward, but backward, unraveling the story of everything, one photon at a time. When we speak of the vastness of the universe, it is easy to picture galaxies drifting like isolated islands scattered randomly across an endless ocean of darkness. But the deeper we look, the more we realize that the universe is not random at all. It is organized into structures of almost unimaginable scale. These are the great patterns of the cosmos: clusters, superclusters, filaments, and the immense cosmic web. To understand them is to glimpse the universe not as a collection of lonely galaxies, but as a grand architecture woven together by gravity across billions of light years. Let us begin with galaxies themselves. A galaxy, like our Milky Way, is a vast system of stars, planets, gas, dust, and dark matter bound together by gravity. Each one may contain hundreds of billions of stars, and yet a single galaxy is only the beginning. Galaxies rarely exist in isolation. Instead, they gather into clusters. The local group, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, is an example of such a cluster. On a larger scale, clusters can contain thousands of galaxies, all orbiting one another in a slow gravitational dance. But clusters themselves are not the end of the story. They gather into even greater structures called superclusters. Our own local group belongs to the Virgo supercluster, a region spanning over 100 light-years. Yet even this is only one thread in a larger tapestry. In recent decades, astronomers have mapped something even more astonishing: the Laniakea supercluster. This immense structure, discovered in 2014, encompasses about 100,000 galaxies, stretching across 520 million light-years. And within it, our Milky Way is just a tiny, almost forgettable dot. Beyond superclusters, the universe forms structures so immense they almost defy comprehension. Galaxies and superclusters arrange themselves into long, thin chains and walls known as filaments. These filaments stretch for hundreds of millions of light-years, threading the universe like veins of light. Between them lie vast empty regions called voids, where there are almost no galaxies at all. Put together, these filaments and voids form the cosmic web, a three-dimensional network of matter that is the very skeleton of the universe. The cosmic web is not just beautiful, it is fundamental. It reveals how gravity, dark matter, and cosmic expansion have sculpted the universe over billions of years. Computer simulations show that soon after the Big Bang, tiny fluctuations in density grew into threads of dark matter, which pulled in gas and dust, forming galaxies along their spines. What we see today, when we map the universe on its largest scales, is the frozen aftermath of that growth. A web spanning billions of light-years, glowing faintly with the light of galaxies, stretching farther than our imagination dares to go.
To give a sense of scale, imagine standing in the Milky Way. Around us are billions of stars. Beyond, in the local group, dozens of galaxies. Beyond that, in the Virgo cluster, thousands. Step back further into the Laniakea supercluster and we see hundreds of thousands. But zoom out still more, and these galaxies, clusters, and superclusters resolve into filaments and walls, forming structures that extend across hundreds of millions of light years. And all of this, the web, the filaments, the voids, is only a fragment of the observable universe. Even more humbling is this. The observable universe itself may be only a patch of a larger, unseen whole. The web we can map may stretch far beyond our horizon, continuing into regions forever cut off from us. In that sense, the cosmic web is not just vast, it is perhaps infinite, a structure without end. And yet, despite its enormity, the web connects us. The Milky Way is a thread in this cosmic fabric. The stars we see at night, the atoms in our bodies, even the light in our eyes, all trace their origins back to this grand structure. The same gravity that binds galaxies into clusters is the force that binds us to the Earth. We are not separate from the cosmic web. We are one of its smallest, most delicate threads. So, how big is the universe really? In part, it is as big as the structures it contains. Galaxies the size of hundreds of billions of stars, clusters that stretch for millions of light years, superclusters spanning hundreds of millions, and filaments spanning billions. It is as big as the web itself, a vast and interconnected architecture woven across the whole of space. And beyond that web, perhaps, lies an immensity we cannot yet imagine. When we ask how big the universe really is, we often turn to the word observable, as in the observable universe. But this word hides a profound truth. The universe may be far larger, perhaps infinitely larger, than anything we can ever see. What we call the observable universe is not a measure of the entire cosmos. It is the portion of the cosmos that the laws of physics allow us to access, the sphere of space from which light has had time to reach us since the Big Bang. Think of it this way. The universe is about 13.8 billion years old. That means light has had 13.8 billion years to travel. But because the universe has been expanding during that time, the farthest galaxies we can see are not 13.8 billion light years away, but much farther. Accounting for this cosmic expansion, the radius of the observable universe today is about 46 billion light years. That gives us a cosmic sphere nearly 93 billion light years across. Within this sphere are hundreds of billions of galaxies, each containing hundreds of billions of stars. It is a number so staggering that even the most imaginative human mind struggles to comprehend it. Yet this observable universe is only a boundary drawn by time and physics. Beyond that horizon, space does not suddenly end. Galaxies do not stop existing at 46 billion light years. They are still out there, drifting in the void, but their light has not had time to reach us, and in many cases, it never will. This leads us to a strange but important idea, the cosmic horizon. Just as sailors once saw the horizon as the edge of the Earth's ocean, our cosmic horizon is the edge of what we can ever see. And just like sailors eventually discovered that the ocean did not end at the horizon, cosmologists suspect the universe extends far beyond what we can observe. The difference is that we may never be able to sail past our horizon. Why? Because the universe is not just expanding, it is accelerating. Driven by the mysterious force we call dark energy, galaxies beyond a certain distance are receding from us faster than the speed of light. No matter how long we wait, their light will never reach us. They are lost to us forever, beyond a one-way boundary of physics. In fact, with every passing moment, more galaxies slip beyond that horizon, vanishing into eternal darkness from our perspective. The observable universe is shrinking in terms of what we will ultimately be able to see, even as space itself continues to expand. This gives rise to a humbling realization. The true universe could be far larger than what we observe. It might be hundreds, thousands, or trillions of times bigger. Some cosmological models even suggest it may be infinite, stretching endlessly in all directions. If that is true, then our observable universe, the 93 billion light-year bubble we so often marvel at, is only one speck, one cosmic grain of sand in an unbounded sea. And the mystery deepens further when we consider the possibility of a multiverse. If inflation theory is correct, then our universe may be only one bubble among countless others, each with its own physics, its own galaxies, its own cosmic horizons. In that case, even calling the universe infinite might not capture the full immensity of reality. We would be speaking not of one cosmos, but of a vast multiverse, a space of spaces with no end at all. But here's the paradox. Though the universe beyond our horizon may exist, it will always remain beyond our reach. No telescope, no spacecraft, no technology, no matter how advanced, can break the limits imposed by the speed of light and the accelerating expansion of space. The horizon is not just a technical barrier, it is a fundamental wall of nature. We are, in a sense, trapped within our observable bubble, forever unable to glimpse what lies beyond. And yet, in that limit lies wonder, because even within our small bubble, our 93 billion light-year sphere, there are more galaxies, stars, and planets than we could ever hope to count. Within this one observable universe, there are enough mysteries, enough worlds, enough questions to fuel human curiosity for eternity. And beyond it lies the unknown, a reminder that the universe is not ours to conquer, but to marvel at. So when we ask, how big is the universe really? The honest answer is this. As far as we can see, it is 93 billion light-years across. But in truth, it is bigger than we can ever measure, bigger than we can ever imagine, and perhaps bigger than even infinity can describe.
We have come a long way together. From the first questions about the size of the universe to the vast horizons of galaxies, dark matter, dark energy, and the unseen realms beyond our reach, we have wandered slowly and carefully through the cosmos. And now, in this final stretch of our journey, we stand at the edge of everything we know, the limits of observation, the boundaries of thought, the quiet place where science and wonder meet. When we began, we tried to imagine the scale of our solar system. Planets drifting in orbits, the sun at the center, distances so large that light itself takes minutes to hours to cross them. Then we pulled back further, to the realm of stars, constellations, and our Milky Way, a galaxy of hundreds of billions of suns. But even the Milky Way, vast beyond measure in our daily terms, turned out to be just one island in a sea of galaxies. We counted further, clusters, superclusters, the cosmic web stretching like threads across the night. And eventually, we arrived at the observable universe, a bubble nearly 93 billion light-years across, filled with galaxies as numerous as grains of sand on all the beaches of Earth combined. Even here, we found ourselves humbled, because beyond that bubble lies more, much more. Realms we will never see, horizons we will never cross, mysteries that will remain mysteries forever.
So what does it mean then to live in such a universe? To be a small creature on a small planet circling an average star in one spiral arm of one galaxy inside an ocean of unthinkable size? Does it make us insignificant, or does it reveal something deeper? Perhaps the answer is both. We are small, yes, unimaginably so. In terms of scale, our entire world is less than a grain of dust, flickering briefly in the darkness. But at the same time, within this smallness, something extraordinary has happened. The universe has become aware of itself. Through us, through our curiosity, through our questions, the cosmos looks inward. We are not outside the universe staring in, we are part of it. The stars made us, and now we gaze back at the stars. And maybe that is the true measure of greatness. Not in size, not in power, but in awareness. A human being sitting in the quiet of night asking, how big is the universe really, carries within that question the light of countless generations, the whispers of all those who looked up before us and wondered.
We will never know the full answer. The universe is too vast, too mysterious, too boundless. But perhaps the beauty is not in reaching an answer, but in the endless act of seeking. Every discovery, every measurement, every theory is just another step on an infinite road. And each step reveals not only the universe around us, but the universe within us, our patience, our imagination, our need to understand. So as we close this long journey, let us pause here at the edge of the infinite. The universe is larger than words can hold, larger than minds can grasp. It is endless, eternal, and still unfolding. And yet, tonight, it is also something simple. The quiet sky above you, the stars faintly shining, the silence wrapping around your thoughts. Carry that silence with you now. Let the vastness settle like a soft blanket. Let the questions rest for a while. You are part of this universe, and in that belonging, there is peace. Good night, traveler of the stars. Sleep well beneath the endless sky. Until the next journey.